introduction. Good afternoon, everybody. James Cross, as Randy said, from Kinectrics. Good, bad, or indifferent, I am a lifetime career transformer guy. It's the only field that I have ever worked in, starting from when I graduated from University of Manitoba a long time ago. And I've worked at transformer OEMs as a transformer designer, and then later with a company called Wideman Electrical Technology, which may resonate with some of you, the world's largest provider of cellulose-based insulation materials. And then most recently at Kinectrics. And always happy to hear. I know Drew talked a little bit about some of the IEEE guides and standards. I'm actually the secretary of the C57-149 SFRA guide that you mentioned, along with Chuck, who's the chair. And I am the vice chair of the IEEE C57-170 guide for transformer condition appraisal. So very plugged into those things. I don't know what you folks might know about Kinectrics, and I'm not going to get into a deep dive here on this. We simply don't have time. Kinectrics had its genesis as the old Ontario Hydro Research Division back in 1912. So our roots, our utility-based roots, we're about 80–85% in the nuclear space and about 15 to 20% in the T&D space. And we're very proud of the fact that of our people, which now number more than 1,200. As you can see here, over 700 of them have technical science or engineering degrees and a lot of advanced degrees. So we have a good bench depth at Kinectrics. We have a lot of different facilities around the world. Picture on the top right is our Kipling campus in Toronto. On that campus, we have something like 25 different laboratories for doing various tests. And then we have these other facilities around the world. So this presentation, the goals here are to demonstrate the critical nature of moisture management in power transformers in terms of protecting your asset from catastrophic failure and for optimizing its lifespan. So it's a critical maintenance activity that you need to be aware of. We want to show the significant impact that moisture has on transformer operation and its potential life, and to show the limitations of, I'll say, conventional transformer drying processes in removing moisture from the paper insulation. And you're going to hear a lot from me in the next 40–45 minutes talking about paper insulation versus oil insulation. And we know in an oil filled transformer, which is what this topic focuses on, the insulation system, quote unquote, is comprised of the paper and the oil together. They work hand in glove to provide the insulation inside the tank. We'll talk about issues associated with how we measure moisture inside transformers, because that is kind of germane to some of the misgivings and misconceptions that are out there. And just to leave you with a taste of all the methods that are available for drying transformers, that low frequency heating is by far the best method for field drying of medium to large power transformers. You know, the threat of transformer failure being caused by moisture is very real. Picture that you see there is of a large generator step-up transformer at a nuclear plant. This was a forensic analysis, failure analysis that Kinectrics was involved in the aftermath of this unit exploding, which is basically what happened. You can see it's this particular unit, it's a single phase core type transformer, about 400 MVA. And absolutely no question, as a result of the failure analysis, that this transformer failed, catastrophic dielectric breakdown due to moisture in the insulating paper. And what's really interesting from my perspective is that this transformer had just been, quote unquote, serviced by conventional oil processing only weeks before this failure happened. So this was not a neglected transformer that just decided to up and fail. It had been receiving regular maintenance testing, regular maintenance activities. Clearly, those, as we will see momentarily, were not effective. The transformer itself was quote unquote middle aged. We can do a furanic compound assay on the oil. It's one of the tests you can do on oil. And from that, we can infer the degree of polymerization of the paper. I'll talk more about that in a couple of slides. But the DP in this case was 700, which is about middle of the road and indicative of, again, what we would consider to be a middle-aged transformer. So it had lots of lifespan remaining and no reason for it to fail prematurely. And there's no doubt in my mind that had this transformer been dried with a better process, for example, low frequency drying, this failure would have been prevented. And this particular utility got really lucky. They had a spare sitting on site that they could quickly move into place. Had that not been the case, those of us in the industry are aware that at the moment lead times for new power transformers are somewhere in the 2 to 3 year range, which is almost unheard of in the industry. But that's where we are at the moment from a supply chain perspective. So it really shows the importance of babysitting and looking after the transformers that you have, because to get a new one is going to be expensive and it's going to take a long time. Continuing with the theme of the reality of the threat of moisture, SD Myers, which is an oil testing organization, a laboratory, and a service company in the US, they have a very extensive internal database from all the oil testing that they've done over the years. And they conducted a survey of that data and found that almost 1 in 10 transformers in that database of 85,000 records had unacceptable moisture levels inside the transformer. Unacceptable being greater than 18% relative saturation. And because Kinectrics is in the nuclear space, we have access to the INPO database, and we searched the OPEX, and there's several instances where nuclear facilities have experienced transformer failures that can be directly attributed to excess moisture in the paper insulation inside the unit. The basis of the moisture problem is this. The insulation system in the transformer, as we've already mentioned, is comprised of paper, cellulose-based paper, and oil. And that cellulose insulation, when it is properly dried and properly oil impregnated, and I guess that's the key phrase, is properly, it is one of the best electrical insulation systems available. Certainly one of the most cost effective. On a dollar per pound basis, it's pretty tough to beat cellulose insulation and oil as an insulation system. Inside your transformer, there are some minor exceptions that have occurred over the years, but I'll make this as a blanket statement. Most power transformers, the insulation medium inside, the paper, the low density press board, the high density press board, these materials are made from 100% cellulose fibers, what we call craft process fibers that are from softwood sources, i.e. pine trees, etc., spruce trees. And as good as cellulose is as an insulation material, its dark side, as I like to call it, is that it is one of the most hydrophilic materials known. It wants to absorb and attach itself to water, or conversely, water attaching itself to the cellulose. And it is extremely difficult in terms of time and energy to separate that moisture from the cellulose insulation. And so that causes, the basis of the problem. For those of you that may be not familiar with kind of the internal guts of a transformer, this is a cross-sectional view of a high voltage winding arrangement. Basically, what I tell folks is that everything that's brown in this picture is cellulose insulation material. You can see inside this lead exit tube here, we can see the copper that comprises the conductor that would be going up to the bushing. And of course, in the winding itself, we see the rectangular copper wires, but even these are individually wrapped with cellulose based paper wrap. And we see all different manner of components here. We see cylinder wraps in the high-low barrier. We see static rings that are made from high density pressed board cores wrapped with paper over that. We see cap rings, angle rings, high density blocks for clamping plates, etc. So bottom line is there is a lot of insulation material inside a transformer that is cellulose. And kind of as a rule of thumb on high voltage, large power transformers, somewhere between 3 to 5% of the weight of the transformer will be in these cellulose-based insulation materials. So it can easily reach up into the tens of thousands of pounds on a large transformer. So what's the problem with having moisture inside a transformer? I think all of us can kind of relate to having a high voltage device and water kind of don't go hand in hand, you know, along the line of the picture that Drew just showed at the end of his presentation there with the guy with the bucket of water. That's not how we want to put out a fire on a transformer. So water is not something you want inside your unit, and it can affect the performance of the paper, the solid insulation. And on the right top of the slide there, you see some classical water treating that's taking place on the surface of the paper. And that's a partial discharge related activity caused by excessive moisture in the bulk of the paper. Similarly, moisture can affect the dielectric performance of the fluid. And by the way, in most of this presentation, I'm really going to be talking about mineral oil. As you probably know, these days there are many alternative fluids that can be used, and each of those reacts somewhat differently to moisture, but fundamentally the same issues are prevalent. But I'm going to be talking specifically about mineral oil filled transformers. One of the things that's not obvious, but to me is one of the most important factors, is that moisture acts as an accelerator of the aging of the cellulose insulation inside the unit. As cellulose paper ages, water is actually produced in that chemical reaction. I'll show you that in a slide in a moment. But it's what we call an auto-catalyzing chemical reaction, and moisture is actually an input to those chemical reactions as well. So having moisture inside a unit accelerates the aging process. HVDC transformers, which are a real special breed of unit used on obviously HVDC transmission systems, affects the volume resistivity of the oil and the paper in the transformer. You know, when we design transformers, conventional transformers, the insulation design is done on the basis of alternating current capacitances and the relative permittivities of the insulation materials. On DC units, we're more concerned about the volume resistivity of the insulation materials used. And again, moisture has a big effect on that. Another thing that's quite obvious is undesirable chemical reactions that can be occurring in the tank. And the obvious manifestation of that is rust. So if you ever open up a transformer and see rust on the inside of the tank, if it's not painted, on the core clamps, on the edges of the core steel, etc., that's a clear indication that we have a moisture problem inside the transformer, because in a properly dried transformer, there is not enough moisture to lead to oxidation of steel that causes rust. Again, maybe something that's not obvious, but very detrimental to transformers is it can affect the loadability of the transformer. You can imagine if we've got moisture in the paper insulation, as the transformer is increasingly loaded, the load increases, the windings get hotter. And, you know, 80, 90, 100 degrees C is not an unusual temperature for a fully loaded power transformer in the windings. And guess what? At 100 degrees C, what happens to any moisture that's in the paper? It boils and it turns to steam, and the steam comes out as bubbles. And bubbles are very bad for obvious reasons. They're an area of very low dielectric strength, and you're going to get partial discharge and quite possibly and quite probably catastrophic dielectric breakdown. In the picture on the bottom right here, we see a disc winding, and we can see some streamer bubbles coming from that, and also some trapped very large air bubbles below the disc. So it's a very real effect. And uh, transformers that have a lot of moisture in the insulation structure cannot be loaded, or should not be loaded, in a way that produces these bubbles. So it's a limiting factor. Moisture can contribute to partial discharge in areas of high dielectric field stress. Again, the tracking that you see in the top right, the classical treating structure, that's an indication of that. And then something that I call bridging dielectric failures occur if you have moisture in conjunction with particles floating around in the oil. And actually, oh, maybe I took those out. I'm sorry, I took that slide out. Well, this is one reason why I always tell folks on high voltage units, you want to, from time to time, get what's called a particle count test on your oil. Because if you get moisture that attaches itself, as it's going to want to because of the hydrophilic nature of cellulose, to any cellulose dust or fibers that are in the transformer, those fibers are going to start to accumulate in the areas of highest dielectric strength in the windings, which is the exact opposite, of course, of what we want to happen. And that's because the water molecules have a net dipole moment, and they want to align themselves with the electric field in the transformer windings. So they will accumulate and ultimately lead to a breakdown. This slide is speaking to the topic I mentioned about loadability. So on the horizontal axis, we see the moisture content of the paper insulation in the transformer, and the hottest spot temperature in the winding, and increasing load. So at some point, the moisture level becomes so high that we cannot tolerate a high temperature in the winding due to that bubble formation. So the higher the moisture, the more that effect is pronounced. This is addressing the point that I mentioned about moisture affecting the aging of cellulose insulation in a transformer. So what we have here on the horizontal axis is the operating temperature of the transformer in degrees centigrade, and the life expectancy of the insulation system on the vertical axis. Notice that that's logarithmic, and it's in years. And then we have several curves there indicating the moisture content in the insulation, from dry on the top right, and then to a 4% moisture content line on the left. And there's just an example. For a given operating temperature, in this case, I've picked 90 degrees C, not an unusual temperature for a fully loaded transformer. If you've got 1% moisture content in the paper, you could say that the lifespan of the paper insulation is going to be about 12 years. Increase that moisture content to 3%, so 3 times the moisture content, you'll notice that the lifespan of the insulation drops by a factor of 6, from 12 years down to 2. So it's not linear, it's a geometric progression. And as mentioned, when we're talking about life expectancy of transformers, it really boils down to the life expectancy of the paper. Anything on a power transformer, almost anything, you can replace while the transformer's in the field. If you've got gauges that are no good, you replace the gauges. If the radiators start to rust, you can replace the radiator. Even the oil, as part of the insulation system, if the oil's gone bad, you can take the oil out, pump it out, and you can regenerate it or replace it with new oil. Two things that are going along for the ride are the core steel and the paper in the windings. And so you really want to be paying attention to making sure your maintenance practices are preserving those two elements as the only two elements that can't be readily replaced. And so when we're talking about paper, again, we're talking about the degree of polymerization of the cellulose molecules in the paper. So we know moisture's bad. We know the effects that it can cause. Where does moisture come from in a transformer? And there are four basic sources of excess water in transformer insulation. The first is when you buy a transformer, a new transformer from the factory, it comes along with a little present. And the little present is some water that's still left in the insulation. And I want to emphasize it's not that the transformer OEM is doing anything nefarious or untoward. As mentioned, cellulose is simply so hydrophilic, it is impossible to remove all the water from the paper. And so there is always some paper, some moisture that comes along for the ride when you get a new unit. Ideally, it should be somewhere in the range of about 0.3% by weight. Depending on the drying process that the factory uses, and they all do different things, it could be higher. It could be north of 0.5%. And factories that do not use vapor phase drying systems tend to struggle a little bit more than those that do. So not all are equal in that regard. Another source of moisture getting into the transformer, well, you can blame some of it on our friend in the picture on the left there, which is a silica gel breather. And silica gel breather is used on a transformer because as the transformer operates, high load, low load, high temperature, low temperature, the oil expands and contracts. And as the oil expands and contracts, we need a way for the gas space somewhere in the transformer, whether it's in the tank, in a sealed unit, or in the conservator tank. In those designs, we need to allow air to come in and out. And we want that air to be dry. And so that we have the silica gel breather. Well, they're a maintenance nightmare. And I can't tell you how many substations I go into where the silica gel breathers have not been properly serviced. And you just know that moist air is going through them into the inside of the transformer. But beyond that, transformers, especially really large ones, they're an interesting product, right? When you go to buy a car, you go to the dealer, you hand them the check, and they give you the keys, and you drive away. A large transformer, it's built at the factory, it's tested, then they take it apart and they ship it to site and they rebuild it on site, and then it has to be re-dried and refilled with oil. And sometimes, more often than not, things like bushings need to be installed, radiators need to be put on. And in those commissioning, we call that the dressing out of the transformer. It's possible for moisture from the atmosphere to get into the transformer, even though we might be being extremely careful, purging with dry nitrogen or whatever. So those operations are an avenue for moisture ingress. Leaks are a third method. And leaking gaskets, rips, pinholes, tears in airbags or air bladders in conservator tanks, if a conservator is equipped with one of those. Weld pinholes. I've seen several transformers over the years I've been in the business where we have porosity in welds, and they allow oil to come out. And I always mention to folks, if you see weeping oil or evidence of oil seepage anywhere on a transformer, and typically if there is any, you'll see the dirt that typically accumulates on a transformer tank, it'll have that wet look. Any leak in a transformer under the right circumstances can be a two-way street for atmospheric moisture to get inside the unit. So you want to treat leaks extremely seriously. And then again, the one that we don't often think of, it's a little bit more nefarious, more hidden, is that the normal, and I want to emphasize this, the normal decomposition of cellulose paper during the natural aging of a transformer produces water. So even a transformer that doesn't have leaks, doesn't have issues with the silica gel breathers, sooner or later that transformer is going to manufacture, if you will, its own moisture inside itself, and so it'll moisture content will start to rise. I already mentioned this, but we're talking about the decomposition of cellulose being an autocatalytic chemical reaction. So the rate of that chemical reaction is determined by the presence of oxygen, heat, and moisture, water. And the more we have of any of those three things, the faster the breakdown reaction is going to occur. And we all know that the chemical dynamics that govern aging are, like any chemical reaction, determined, the rate of the chemical reaction is determined by the Arrhenius equation. So a 7 degrees C increase in operating temperature of the transformer halves the life of the insulation system. Conversely, running 7 degrees cooler doubles the life of the insulation system. So it's very strongly thermally driven. And what I mean by autocatalytic is water is an output of those chemical reactions, but it is also an input, almost like a nuclear reaction where you have a few neutrons that hit other uranium atoms and they make more neutrons. And right, that's where the atomic blast comes from, is that runaway chain reaction. So as the cellulose breaks down, I'll show you a picture in a minute, but what we have is the polymer of the macromolecule starts to get broken up into smaller pieces. And every time that chain scission, as we call it, occurs, we get water given off, and in the oil, we start to see furanic compounds. Okay, so here's our friend, the cellulose molecules. That's what the paper inside the transformer is made from. It is actually a sugar. Cellulose is a sugar molecule. And those sugar molecules like to join at their reactive ends. You see the OH end of the molecule joining with an oxygen bond. So each one of these cellulose molecules is called a monomer. And when we join two together, we now have a polymer. And cellulose is the world's most common naturally occurring polymer. You know, normally when we talk about polymers, we're thinking about synthetic polymers, which are plastics. Cellulose is a natural polymer. And the number of these cellulose monomers that we have joined together is what we call the degree of polymerization. So right now on this picture, we have a degree of polymerization of 2, because I have 2 glucose monomers joined together. New paper, brand new, typically has a degree of polymerization somewhere between 1,000 and 1,200. End of life is deemed to be somewhere around 150 to 200. Different people make arguments for different numbers, but anyway, that's kind of at a high level, those are the endpoints. These are the chemical reactions. I'm not a chemist. I'm just a poor electrical engineer, so forgive me if we have any chemists in the crowd. But here we have our cellulose polymer. We have the presence of water, which attacks this oxygen bond here, and we have a chain scission occurring where the molecule breaks apart. And the hydrogen and the oxygen from the water molecule contributing to the breakup of the chain scission and attaching to the ends. So now we have a lower degree of polymerization than we had before the breakdown. And these chemistries are affected by temperature, as mentioned. So you'll see that as an outcome of the decomposition, we get more water, HOH, H2O, 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 and carbon monoxide, and also some carbon dioxide. Okay. Those are places or processes that produce water in a transformer. Where is the water in a transformer? Well, this is interesting because on the left side, you see a pie chart that shows the weight distribution of the insulation in a transformer. And in a paper oil insulated transformer, in rough numbers, about 90% of the weight is the fluid, it's the oil. And only 10% of the insulation system is actually comprised of the cellulose materials, whether they're winding like conductor wrap, or what we call thin, which would be like your caps and collars, and thick, which would be like your core clamping plates, etc. But as far as the water distribution goes, by far, most of the water is in the paper, in the cellulose, not in the oil. You know, growing up, we're always taught water and oil don't mix, and fundamentally that's a true statement, but at a molecular level, there is some dissolving of water in oil, but it's very, very small. So even though oil is 90% of the weight of the transformer, only 1% of the moisture is actually in the oil. It's in the parts per million range, right? All the water is in the paper and the press board. And this is where the problem starts to come when we talk about removing moisture from a transformer. It's actually very easy to remove moisture from the oil, but that's not where the water is. The water's in the paper, and it's really hard to remove the water from the paper. That's the gist of it. The moisture inside a transformer is constantly migrating. I call it moisture partitioning. It's constantly migrating between the oil and the paper. And that is a temperature driven process. So as the temperature drops, moisture is going to want to come out of solution from the oil, and it's going to get pulled into the paper, as we see in the diagram on the left. As the temperature rises, conversely, moisture is going to get pushed out of the paper and it's going to get absorbed into the oil. And so we see a shift of moisture from the paper into the oil. Okay. We also know heat rises in everything, but in a transformer, the same is true. The top part of a transformer, the top part of the core coil assembly is always hotter than the bottom, which means by this process, the bottom part of the core coil assembly is always going to be wetter, have more moisture than the top part. Okay. And so this partitioning is why it is so critical, so important that when you take an oil sample to do tests at a laboratory, you must record the temperature of the oil, the sample that was taken, because that's the only way that we can look into this partitioning. Again, just to kind of prove the point, here's a moisture profile inside a transformer. In the middle here, we see the windings. And at the top of the winding, where it's operating at 98 degrees centigrade, the water content in this region is only 0.7%. But at the bottom, where it's only operating at 60 degrees centigrade, in this case, an outside winding, the moisture content is much higher. So we need to be very careful when we're talking about moisture content in a transformer. And when you're measuring something to determine moisture content in a transformer, we're always going to be talking about the average moisture content. And you need to recognize that there's going to be places in the transformer where the moisture level is higher and places in the transformer where the moisture content is going to be lower. This chart is, depending on which version you look at in history, it's either a Jeffreys curve or an Uman curve or a Weidman curve. And what it is, it's relating the moisture content in the oil with the moisture content that is in the paper. And we see different operating temperatures for the transformer on these different lines. And I want to emphasize that these charts assume thermochemical equilibrium inside the transformer, constant state of affairs, if you will, which almost never happens. Why? Because transformer loads are not constant. And even if the load is fairly constant, the operating temperature during the day, we have higher daytime temperatures, lower nighttime temperatures. We have hotter temperatures in the summer, cooler in the winter, etc. You get the picture. So they're in a constant state of flux. However, it's still instructive to kind of look at what these curves tell us. And so if you were to take a case of a transformer operating, well, let's just pick the bottom one because it's easy. It's almost linear, 100 degrees C. If I have 20 parts per million of oil, moisture, pardon me, in the oil, I can look across and I see, oh, my moisture content in the paper is about 0.5%. Okay. If I now look at room temperature, look what happens. Water content in the oil of only 10 parts per million at 20 degrees C. So now I'm coming up here and coming across, implies or infers 4.5% moisture content in the paper. Very, very different. So even though the parts per million is less, because we're talking about a lower temperature, it has a much greater effect. And so, again, not to beat it to death, but this is why it's very critical that when you do oil testing in a unit, you absolutely need to know the temperature of the sample at the time it was taken. And I will tell you, just kind of before I forget, to go back to my example of the failed GSU on the opening slide, that 400 MVA single phase unit. When I got the phone call that day from the utility that they had a failure and they wanted some help in finding out what was going on, I said to the engineering supervisor, hey, this was a Sunday afternoon when I got the call. I said, Monday morning when I'm in the office, I'll pull the oil test records and we'll take a look. And which I did. And the oil Carl Fisher test, ASTM D1533, showed 8 parts per million of moisture in the oil, which kind of on its own, it's a single digit, right? 8 parts per million. It doesn't sound bad. But this unit operated at a temperature of about 42 degrees centigrade. And if you take that 8 parts per million now with that temperature knowledge, you're over 2% here. Well, you're 2.5%, almost 2.3% moisture content. So it has a big impact. And this was a 230 kV unit, and you do not want to have anything near 2% moisture content in paper in a unit of that voltage class. So right away we had the early hint of what caused the problem. So if we know moisture's bad, how dry do we really need it? And this is an interesting question because there actually is nothing directly in the IEEE standards at the moment that say what's good and what's not good. There's actually a working group right now that's delving into this question. But we do know some benchmarks, and a benchmark would be a new transformer. So if you've got a transformer greater than 69 kV class coming from a reputable factory, one that has, for example, a vapor phase dry out system, we know that the moisture content in the paper is going to be 0.5% or less. And below 69 kV, where vapor phase might not be used in the factory, we'd still only be looking at 0.5 to 0.75% moisture content. So those are kind of numbers that we'd associate with a new transformer. As the transformer ages, as we've discussed, those numbers are going to go up. So this is kind of the lower point. We can back into some numbers, if you will, through IEEE C57106, where it talks about permissible values of water content in the oil. So we could use our friend the Uman curve and use the parts per million of the oil at a temperature and come up with associated moisture content in the paper. And you see some numbers here. A lot of utilities develop OPEX over the years, have their own limits from their own engineering standards. So this is some guidance in the absence of that data. How do we measure moisture content in a transformer? And this is the $1 million question. And I tell folks, anybody that devises an instrument that allows you to directly measure the moisture content inside a transformer is going to be a millionaire, because all of us in the business would love to have that capability. From a strictly scientific perspective, and I want to emphasize that, I'm not promoting that we do this, but from a strictly scientific perspective, the most accurate way to measure moisture content in a transformer is to drain the oil down, go inside, take a paper sample, and test it. And that will give us the moisture content of the paper. We would put the paper in an oven, dry it down, measure it before and after the drying process, and we'd get weight by weight. Not recommended. This is very invasive. It's potentially very damaging to the transformer, and it's a lot more likely, in my opinion, that you're going to cause a problem in the transformer than solve one. So what do we do instead? Well, kind of the industry standards. We take an oil sample and we do what's called a Carl Fisher titration test, which goes by the ASTM test procedure D1533. And that gives us the parts per million of water in the oil. Okay. And if I've been smart and taken the temperature of the oil sample, I can go to my Uman curve and I can get my moisture content in the paper. Another technique that is used, and I don't know if Chris talked about that because I came in a little bit late into his presentation, but there's a newer test that's been developed called dielectric spectroscopy, otherwise known as dielectric frequency response, which is a power factor measurement taken over a wide frequency band from like 0.1 millihertz to 1 kilohertz. And the instrument that performs that measurement has a database built into it, and it'll take the curve that results from that measurement, and it will give you an estimate of the moisture content of the paper insulation inside the transformer, which is the colored chart that you see on the right-hand side. In this particular case, this was a Mager IDAX that was used to take this measurement, and it comes back and it says, okay, here's your moisture, your power factor, your dissipation factor, 10 delta, and here's your associated estimated water content. When we're processing transformers, drying them out, and we have the oil removed, what we would normally do at that point is do what's called a dew point measurement of the gas space. So you have to wait for thermochemical equilibrium to take place, which is typically about 24 hours for a big transformer. And then you take a sample of I'll say the gas space inside the tank, and you measure the dew point of that. And that dew point, by using something called a Piper curve, you can get the moisture content of the paper inside the transformer. So these are all indirect methods is the point. And lastly, there's a lot of monitoring equipment on the transformer. I know our friends at Dynamic Ratings have some methodologies for putting monitors on equipment or integrating data from such monitors that can give you an idea of the moisture content of the paper and how it's changing as a function of time. And this is an evolving marketplace that I would say has a lot of hope for the future for our industry. I'm not going to get into this other than to say, to remove moisture from cellulose paper, you need three things. You need a moisture gradient, you need a drier area, and a wetter area. You can't just kind of magically poof all the moisture out. You can only pull moisture from a wetter area into a drier area in the bulk of the paper. You need a temperature gradient, i.e. heat, and you need a pressure gradient, or conversely, a vacuum gradient. Okay. And I guess the key takeaway here is that these time constants are for cellulose paper, particularly in the field where the paper is already oil impregnated. These diffusion time constants are very long, like weeks and months, because the water molecules now need to migrate through the pores of the paper that are impregnated with oil. And so surface drying paper happens pretty fast, but to dry the bulk of the paper takes a much longer time. So how do we dry? And I'm just doing a time check here, so we'll wrap it up in the next 5 or 10 minutes. There's two ways that you can fundamentally do it. You can attempt to dry the paper insulation. And again, I want to remind everybody, that's really the objective here. We know that the water, whatever water's in the unit, is in the paper, not in the oil. So we can attempt to dry the paper by drying the oil and hoping that the moisture is going to come out of the paper into the oil where we can pull it out. Or we can dry the insulation directly. The problem is that can't be done with the transformer energized. By attempting to dry by drying the oil, this is just using a vacuum degasifier, an oil processor. Okay. And you connect up your oil processor, you recirculate hot oil through the transformer. The oil purifier is going to heat up the oil to about 65 C. We don't want to go up much higher than that because we'll start to damage the oil. And over time, we will pull the moisture out of the oil. But because of those longer time constants, we're not really attacking the moisture that's in the paper. The problem is, how are we going to measure the moisture content? Well, often there's a meter on the oil processor that will say there's so many parts per million of water in the oil, or maybe we're going to do some other indirect test here. But those are going to show that the unit is dry when it is not, because we're not looking at the moisture content of the paper. They're only looking at the moisture content of the oil. And the problem with this methodology, again, to dry cellulose, you need to simultaneously apply heat and vacuum. You need those two gradients. And in this particular case, because we have not taken the oil out of the unit, the paper is not exposed at all to vacuum. It's covered with oil. So it's not very effective. Oh, these. Sorry, there's a variation on that theme, which I call a rip and dump. And that's where you connect an oil processor, use it to push heat into the transformer, and then you very quickly pull the oil out and apply vacuum. So now you've got hot paper and vacuum. So you kind of have heat and vacuum at the same time, except we're not putting heat in while we're pulling vacuum. And this is where the problem comes, because as the water starts to come out of the paper, it gives up its latent heat of vaporization, which for water is a very high number. And so very quickly, the temperature will start to drop. And believe it or not, I've seen cases where so much heat is given off through the latent heat of vaporization of the water that ice actually forms in the core coil assembly. So you have to be very careful how long you pull vacuum. You have to monitor the temperature constantly to make sure that you don't get into a region where icing is going to happen. And again, this is because we're not applying heat and vacuum at the same time. Lastly, you can try and dry the insulation directly. And in the factory, that can be done using something called a vapor phase dryout system. And I'm not going to get into that because we could spend a morning or an afternoon just talking about vapor phase. But I'm going to talk a little bit about low frequency heating. And in a low frequency heating system, what we do is we pull the oil out of the transformer. We short out the transformer like we were going to do a heat run or a load loss test, impedance measurement. Okay. And we apply a voltage to one of the windings, which is left open, to get a circulating current going through it. And just like in a heat run or a load loss test, the I squared R losses in the winding manifest themselves as what? As heat, because we're passing current through them. And so we now have a situation where we have vacuum and heat constantly being produced inside the winding at the same time, which is the optimum situation, heat and vacuum simultaneously. Okay. The analogy that I like to give folks is it's like cooking a chicken at home. You have two ways you can do it. You can do it in the microwave or you can do it in the oven. If you put it in the oven, you have to heat the oven up to 400 degrees or whatever, and you wait for it to warm up, and then you put the chicken into it, and you have to wait for the heat to get into the chicken to get our 160 degree safe temperature, right? In that scenario, you're trying to push heat into the chicken from outside. If I put it in the microwave, I turn on the microwave, and the RF energy in the microwave heats the water molecules of the chicken directly, and it heats itself from the inside out. Okay. And so it's a much faster process. So this is kind of the same. These other techniques using an oil processor, you're trying to push heat in from outside. With low frequency heating, I'm generating the heat right where I want it, which is in the windings of the transformer. So the advantages are that we get very fast, very deep drawing of the bulk of the paper, not just the surface. The transformer heats itself from the inside out. All windings are heated uniformly, and it's very energy efficient. And most importantly, because I have good control of this process, there is no damage to the paper insulation. I'm not going to over dry it, which can lead to loss of degree of polymerization, believe it or not. Just to kind of put this into context for you, this is not a graph, this is a data visualization tool. um, Different drawing methodologies that you could use on a transformer. And this is based on real data, by the way. This is the time to dry out a 400 MVA transformer that has 14 tons of insulation in it, from a starting moisture content of 3% down to 1.5%. So I'm only taking half the water out in this scenario. If I use an oil processor only, 6,000 liters per hour, that's a pretty big oil processor, putting oil out at 50 degrees C, you can see here that the time to achieve that moisture reduction is, this is in years, logarithmic on the vertical axis, 0.1, 0.2, 0.3, it's 115 days roughly. If I do the rip and dump, which is the modification, it's better, significantly better, but still 0.1, 0.2, and change 0.23, 76 days. If I do low frequency heating coupled with the hot oil spray, 0.01 years, 0.2, 0.2, 9 days. Order of magnitude difference in effect. And at this point, if I ever have folks that I'm talking to that are on the maintenance side that do this kind of work, they'll say, well, that's crazy. Nobody leaves an oil processor connected to a transformer for 115 days, or 76 days for that matter. And you're absolutely right. And you're not drawing the paper and the insulation, you're only drawing the oil. There's some math, which I'm not going to go through. You folks are going to get this presentation from Randy when we're done here in a minute, and you can go through the math yourself. But this kind of is a cocktail napkin rough calculation to justify where these numbers are coming from. And you can see the bottom line here through my various assumptions and mathematics. The time to remove the moisture for this particular case is 53 days. And that's because of these very, very long diffusion time constants to move the moisture through the paper. To go back in summary here to the failure at the beginning, and kind of with everything that we've talked about, this is a cross-sectional drawing of that single phase generator step-up transformer. We now know where is the moisture going to be the highest? Well, in the coolest part of the core coil assembly. In this particular case, this was a directed oil flow pumped unit, 230 kV, so it had 7 wraps in the high-low barrier. These wraps are not near the conductor of either the LV or the HV, which are heat producing sources. So this has high velocity oil going through it. As I already mentioned before, the oil was at 42 degrees centigrade. And so this is the coolest part. And sure enough, the transformer failed from the LV through the high-low barrier wraps to the static ring at the bottom. This is center fed HV to the bottom static ring at the bottom of the top half of the HV winding, if that makes any sense. So that kind of jives. And in this case, because it was a forensic analysis, we actually did take paper samples, and the paper samples jive very nicely with the dielectric spectroscopy number and the other assays that we did to show a moisture content in this area of around 3%. So there's some lessons learned from this. So I always tell folks, when you're looking at moisture content in a transformer, take a holistic approach. Don't just rely on the moisture and oil data. Do dielectric spectroscopy at a maintenance outage when the opportunity presents itself. Don't look at snapshot data at a point in time. Look at trends. When you're looking at DGA or oil test data, you always want to be looking at the trends. And be aware of the limitations of oil processing as a means to dry out transformers because of how we measure moisture content in a transformer. I can guarantee you that in the 8 weeks before this transformer failed, they hooked up a ginormous oil processor, ran it for 7 or 8 days, and the water content instrument on that oil processor would have shown that the oil that was being circulated through the processor would have had a moisture content probably of around 2 parts per million. And they declared victory and moved on. The problem is that's the oil. We're interested in the paper. And had they done other measurements, and by the way, they did do a dielectric spectroscopy, and the dielectric spectroscopy showed after the oil processing, the transformer was still wet. I don't think the people involved knew what the significance of those numbers were, and had they would have dealt with it. As a recommendation for big high voltage units, we are, and where time is a limiting factor, like an outage at a generator plant, a nuclear power plant, to look at low frequency heating as the preferred drawing method. And we are in the process of acquiring what's going to be the largest low frequency heating system in North America. We actually have a smaller unit that we call Mini-Me already. This one's going to be considerably larger, and it'll be capable of drawing transformers in the 1000 MVA 3-phase range. So we will be addressing wet units in 2024. That's it for me. Again, those are just some of the areas, touch points that Kinectrics has in the transformer side. Those are topics for another day, and hopefully Randy invites us back. And there's my contact information for any questions that anybody might have offline. And Randy, I don't know if we have time for some questions now, but I'm happy to undertake some.
Okay, thank you very much, James. Of course, you're always invited back. You've always been invited, and you're always invited back to participate with us.
Thank you.
Yeah. The Electricity Forum and Kinectrics have a long history, many, many years, helping each other. Okay, first question. Can a protection relay trip or alarm when the transformer indicates the presence of moisture?
Well, I'm still so caveat right off the bat, I'm not a system protection guy. I'm a transformer designer. But I would say that if you've got a protective relay, like a differential relay already operating, you're already in fault mode. Could moisture have caused such an event? Absolutely. But the horse is already out of the barn at that point, is the way that I would put it.
Mm-hmm.
Now, monitoring system, different kettle of fish. If you've got a Callisto or any of them, and I'm not pushing them, but Visala, whatever dynamic ratings might have on the moisture side, those instruments will give you a leading indication that you're headed to a problem on the moisture side. But protective relays are after the fact.
Okay, good answer. Would you recommend oil sample be taken in summertime?
So it depends where we're talking about, because if we're talking about transformers in Arizona, I don't think it really matters. If we're talking about Gillum, Manitoba, at the HVDC generating station up there, I would say, yeah, summer's preferable. Why? It's always better to take oil samples warmer rather than cooler, because we have more mobility of the water molecules. We have a greater likelihood of achieving that thermochemical equilibrium that I mentioned, because chemical reactions are accelerated with temperature. I think you want to be very careful taking oil samples at very, very low temperatures. And again, if I can just back up to kind of further that, if I go back to my Uman curve, look at what happens at 0 degrees C, 10 degrees C, even 20, which is room temperature. These lines are approaching a vertical line almost. And so a very, very slight difference in parts per million content of the oil has a massive impact on using this curve to infer the moisture content of the paper. So if you start to get down below 20, you've got to be really careful in interpreting the results.
Okay, next question. Can I use different laboratories for moisture test results, for transformer oil test results? Or should the same transformer use the same lab to get the same results? Are all labs the same?
So I'll answer the question two ways. All labs should be performing tests to a defined test standard, whether, for example, it's the ASTM D1533 Carl Fisher for moisture and oil, or the ASTM D1816 for dielectric breakdown, whatever. those ASTM test plans, test standards, have a paragraph at the end of them that talks about interoperator accuracy, reliability, bias, and things like that. And any reputable lab should be able to reproduce those results based on that test standard. And you should see very, very close results in between labs. Or even think about it, even in a given lab, it's not, you know, it's not Bill Smith that's necessarily doing the same test. Some days it's Bill, some days it's Janet. And so there has to be even the chemist that's doing the test. As long as you follow the test protocol, you should achieve accurate results within a certain narrow band. That said, consistency is a virtue. If you've got a lab that's working for you, why change? Continue to use them. So I think that's a matter of practicality more than anything. Technically, there's no reason why any lab that's reputable shouldn't give you the accurate results on any test method. And by the way, there are test standards that can be sent to a lab, for example, that has known water content in it, so that you can kind of test the lab, if you will, for accuracy of their results.
Okay, what is the long-term benefit difference between periodic testing and live online testing, live monitoring?
So I'm going to assume that we're talking about online monitoring of moisture content versus
as opposed
periodic.
to taking periodic manual tests.
So my first part of the answer to that is I would always do both. I would never just rely on a monitor. And if you've got a monitor, use, again, as I said, take a holistic approach. Use all your data sources to make decisions relative to your asset. I don't think it should be one or the other. Periodic oil sampling is just that. It's typically once a year. Stuff can happen the day after you take the oil sample. Online is 24/7, 365. I can tell you though, and I'm not speaking so much about moisture. I've done a number of forensic studies where transformer failed, and the monitor that was on the transformer clearly showed 2 hours, 3 hours before the failure occurred that there was going to be a problem, but that was at 2 a.m. and there was nobody there to listen, so to speak. You know, if a tree falls in the forest, right, and there's nobody there to hear it, does it make same kind of a thing? So online monitors are great. I support them, but you have to bear in mind that there's limitations on that as well. If you want to rely on those, you better have a push system that's going to notify somebody that a failure could be imminent. You're not necessarily going to get a week's worth of warning. It could be hours. Maybe not so much for moisture, but partial discharge, I've seen that.
Okay, that's great, James. Thanks very much. Thank you to all of you for staying to the end of this forum. I'm glad that you were with us. I hope you got the information that you were looking for. As I mentioned in the beginning of our forum today, I'm going to send an email to all of the people who registered for this live online transformer forum with links to the presentations to download. And we'll also have links to the videos. We're going to have each one of all of these presentations were recorded, and we'll post the videos to our video section of our website, and we will send you links to those videos so you can watch them again. So thank you very much for attending, and we'll see you next year.